Okay. Unlike the previous talk, we're actually a lander, not a rover. We hold still. InSight's a little bit different than a lot of the other things that you've heard about through the course of the day today. We've now been on Mars for about 2 years. We landed in November 26, 2018. So we're coming up on 2 Earth years, which is, we actually just passed one Martian year yesterday or the day before. So we've been now on Mars for a full year. Unlike a lot of the other missions that you've heard about or are thinking about, we're not really all that concerned with the surface of Mars. We're really trying to figure out what's happening deep inside Mars. We're a geophysics oriented mission, and we want to know about the Mars core. How thick is the Mars crust? What's happening inside Mars mantle? And so it's a little bit different. I list authors on the title slide of talks all the time, and so this first slide is just people who were pretty instrumental in showing figures that I'm showing today. But that's the short list. The long list is our science team, and this is just mainly the science team that's neglecting all of the wonderful operations engineers and everything that takes to make a mission work. So I always want to say that, when I'm talking, you're hearing from a whole lot of other people. It takes a lot to make some of these missions go. So what are we doing in InSight? How is InSight, what is our overall aim here? And in a lot of ways, we're kind of just following in the footsteps of what was done more than 100 years ago on Earth. So around the turn of the 20th century, we finally got to the point where we had good enough seismometers that we can measure earthquakes that happened all over the world at any location around the world. And so we started seeing waves that went through the middle of the planet. And that opened up a new era for understanding what was happening inside Earth, to get to the point that all of the cartoons you see of what Earth looks like when you cut it away, and you see crust and mantle and core, inner core, outer core, all of that really happened in the beginning of the 20th century with the onset of really good seismometry. And so, we're asking questions like, how thick is the crust? What's happening inside the rocky layer below the crust that we call the mantle? How big is the core? How dense is the core? What's the state? Is it liquid or solid? All of these questions we asked about Earth in the early 20th century, and started really telling us about what was happening on our planet. We moved on in the late 60s and early 70s, and we put instruments on the moon with the Apollo missions. And that followed a similar path. We had, from 1972 to 77, we actually had 4 continuously operating seismic stations recording moonquakes. And those have informed what we know about what's happening inside the moon, although it's a much more challenging environment, and we only had 4 seismometers instead of the many, many, many seismometers we have on Earth. And so InSight was, the goal was to, really take that and move that to Mars, so we could go beyond our cartoon pictures of Mars that have huge uncertainties about how big the core is, how thick the crust is, and nail it down. And then that lets us understand more about how all of the rocky planets develop. Because, at this point, if you say you want to understand how terrestrial planets, rocky planets like our own, are formed and evolved through time, we only have one data point for the most part, our own. And so by doing this on Mars, we can look at how this happens for any terrestrial planet. So how were we planning to go about doing it? Well, we had 3 major instruments that were planned for this particular mission. Over here on the left, we have, I've got my camera positioned so that I can't see my own screen. Let me move things around a little bit. Over here on the left, we have the seismic instrument, which we call SEIS, the seismic experiment for an interior structure. It's hidden underneath a wind and thermal shield, which I'll get to later. But this is the instrument that I'm mostly interested in. This is the one that's measuring the vibrations of the ground, which we can interpret as Marsquakes. But we also have 2 other instruments. We have the heat flow and physical properties probe, which was designed to reach down to 3 to 5 meters depth with a mole that's shown down here. We'll come back to that later. So far, we've made it about 40, I believe 46, 47 centimeters. There's been challenges associated with that, but the design here was that the mole would go down and then the tether behind it would have temperature sensors that could tell us how the heat is coming out of the inside of the planet. And then finally, using the medium gain antennas that use X-band radio waves to communicate directly with Earth, we can actually do very detailed, effectively range finding, and look at very small changes and how Mars's rotation axis is moving and wobbling through time that actually tell us a lot about the core of Mars. We have a lot of other supporting sensors though that go into this. We have lots of cameras. Well, we have 2 cameras. We have the instrument context camera, which is sitting under the deck and is always looking at the same view. It's a fisheye view of where our instruments are. And then we also have the deployment camera, which is on the arm, which we can point where we want to. We have wind sensors, we have a pressure sensor, we have a magnetometer hidden under the deck here. And all of these things are designed in order to support the main payload, because it turns out a seismometer is a really sensitive instrument, which means it's really sensitive to lots of things like wind and pressure changes and magnetic variations. All of those things affect the seismometer. So we want to measure them really carefully to know what we're looking at with the seismometer. But of course, we can also use that data to do science on its own. So as I said, we landed November 26, 2018. We actually took off from Vandenberg on Cinco de Mayo in 2018, which was exciting to go theoretically see a launch. It turns out Vandenberg is a really bad place to see a launch in the early morning hours because there's this huge marine layer. So there was absolutely nothing to see, but we did launch. And then roughly 6 months later, we landed. And this is one of the first views we took of underneath the lander. So you can see we have these retro rockets underneath that pulse and actually dug us a few holes in the ground so we could see what the nearer surface soil looks like. It turns out it makes these relatively sharp-sided pits, which actually tell us something about the cohesion of the ground, which I'm going to come back to later when I'm talking about the mole. Over here is the topography of Mars. We landed right here on Elysium Planitia, which is basically almost due north from what Abby was just talking about, Gale Crater, where Curiosity is doing its exploration. We chose this landing site because, as our landing site specialist Matt Gollenbeck said it, it's smooth, flat, and boring. We're not trying to drive anywhere, so we weren't looking for interesting features. We just wanted to make sure we landed safely, and hopefully there weren't too many rocks around so that we didn't have to worry about where we put our seismometer, and hopefully the mole could reach its desired depth. So those were the main characteristics. We also had to be near the equator because we're solar powered, unlike Curiosity. So we needed to, if we want to run year round with solar power, we needed to be near the equator. Here is one of our earliest views from the HiRISE camera on the Mars Reconnaissance Orbiter. This is, we're this kind of greenish feature in the middle that kind of looks a little bit like a Mickey Mouse there in the middle. The two spots on either side there are the solar panels, the main decks here in the middle, and this really bright spot down here is actually telling me that this was the second image taken of us when we'd already deployed the seismometer on the ground. It's actually covered, this was before we put the wind and thermal shield on, and the thermal covering on the seismometer itself is very reflective. So it actually saturates that one pixel right where the seismometer is, which is just shocking to me how great of images the HiRISE camera gives us, that you can see this sort of feature. You can also see how we change the ground around us in the process of landing. So I wanted to kind of give a tour through all the various different instruments that are on the mission, and some of the results that can come out of that. So so first is the meteorology suite, the wind and pressure sensor. So you can see here, this is what the Twins weather wind sensor looks like. There's actually two booms that look like this. They measure the wind speed and direction at all times. We also have the pressure sensor here. You can see what it looks like. It's actually contained within the guts of the lander, but there's a pressure inlet on top that lets us communicate with the atmosphere. Looking at the pressure sensor, you can see this is just for the first 200 sols of the mission, but you can see that the overall pressure actually varies. This is because as the seasons of Mars vary, the amount of carbon dioxide that is deposited on the polar caps varies, and so this causes a noticeable change in the atmospheric pressure on Mars as you go through a seasonal cycle. When there's for the atmospheric scientists, this has been ground truthing of a lot of waves that have been modeled in the atmosphere, but hard to observe because there wasn't a long-term continuous high rate measuring system. And so there are waves that are seen propagating through the atmosphere. We see lots of these little dips. This little spike down here, that's actually a dust devil, or we usually just call them vortices. The reason why I tend to not call them dust devils is because we've tried to take pictures of these lots of times and we've never seen it. I think what we understand is they're not picking up that much dust, and so they're not visible to our cameras. Unlike that wonderful movie that Abby showed of a dust devil captured by Curiosity. But we see lots of vortices. These are just these little swirling low pressure systems that cross over our pressure sensor all the time. There's a lot of potential features that the atmospheric scientists can look at based on these weather data. And if you're interested in looking at basically a continuous high quality weather station on Mars, if you can go to the Mars Weather Service page on mars.nasa.gov and get an update like this. This is today's report, which is actually showing data from yesterday, but you can see it was it got up to a balmy 4 degrees Fahrenheit yesterday, and dropped as low as -140. It's pretty chilly there on Mars. If you go to this page, there's also some plots of history of wind speeds, etc. So for the weather nerds out here, that can be fun. The magnetometer has produced a lot of interesting results. One of the most notable ones, which was not necessarily expected, but not necessarily surprising, when we looked at the continuous portion of the magnetic field, which is actually related to how much the crust below us has been magnetized. It was about an order of magnitude higher than was measured from orbit. What this means is that the crust in this area is varying on length scales shorter than about 150 kilometers, because if it with those relatively short wavelength variations, you can't see those from orbit. This is interesting, as other people have pointed out, when we were talking about habitability. Mars does not have an internally generated magnetic field. And so this crustal magnetization is remnant magnetization from very early on in Martian history when it did have a magnetic field. And so that's interesting information. And we also can see lots of time varying. Over time, we are hoping to use these time varying magnetic fields to actually do magnetic sounding of the interior, which gives us basically electrical conductivity as a function of depth. That's an ongoing process, and it's aided by times when we have close overflights of the MAVEN mission, which has an orbital magnetometer, so we can see the source of the magnetic variations coming from the sun, and then see how they're measured at our landing site, which lets us sound how the interior is being affected by those varying magnetic fields. We're actually coming through a nice time right now when MAVEN is doing overflights of InSight on a fairly regular basis. So there should be more data coming out on this. In the next month or two, there'll be progress made on this front. We also have the cameras, like I said. Over on the left here, this is actually the first image we had that came down from the mission. This is with the instrument context camera, still had the lens cap on, and you can see all the gunk on this image. That's from the landing process. Fairly soon after landing, we popped off that lens cap, expecting everything to clear up. it actually looked like this. It turned out a lot of the gunk got in behind the lens cap. That was unexpected, but ended up being not a huge deal because over the course of our mission, all of that gunk has fallen off, and we actually get quite clear images with the instrument context camera now. And we've taken lots of other pictures of our area around us, and then science panoramas all around. The geologists love looking at all these rocks and naming them, and looking for wind shaped formations on the ground. This has been that's kept a lot of people busy looking for all of this. This is what I was saying. The instrument context camera has cleared up over time. You can see there's very little gunk on it now, and now it always sees us looking out at our seismometer and the HP cubed instrument here out in our area of work. On the main instruments, the first one I want to talk about is the RISE, the radio science portion of the mission. And in this case, what we're doing is doing very precise range finding with the radio transmissions direct to Earth from our lander. And basically what we're looking at are how the spin axis is varying over the course of our mission. There's a very slow change that's called the precession. This is basically the rotation axis slowly rotating around relative to the sun. Over time, that takes about 165,000 years, but over the course of our mission, we can actually see those small changes because the RISE experiment is so precise. And that gives us information on the state of the core, whether it's liquid or solid. And then there's a smaller wobble superimposed on that very long-term motion that we call nutations. And this actually tells us a lot more about the size of the core and the density change between the core and the mantle. The analogy I always like to use, these little wobbles are kind of like when you shake a milk jug and then you feel the wobbles it does afterwards. Those wobbles afterwards tell you how much milk is in the jug. So this is the analogy we're looking for. We're looking at these very small wobbles that tell us about the inside of the planet. And the way this is actually done is that we do communications X-band a few times a week, half an hour to an hour of just communicating back and forth between the deep space network and our lander. For those who aren't familiar with the deep space network, these are great big antennas, arrays of antennas scattered around the world. We have 3 sites, one out in the Mojave Desert in California, one in Spain, and one in Australia. And the biggest antennas are 70 meters, which is huge. They're shocking when you see them in person. So already we can say that the improved precession estimate we've gotten from the mission has confirmed that Mars core, at least as an outer core, possibly as the entire core, is liquid. It is not a completely solidified core. Those smaller wobbles, we're still increasing the precision on those measurements. But what we've already done is shown that the core is likely larger than 1,800 kilometers, which was towards the upper end of the estimate. So we're narrowing in on the size of the core from this data. And right now is the time period when the geometry is best for making these observations. So and we anticipate this making rapid advances over the next few months. Moving on to the seismometer, it turns out it's quite a challenge to operate a seismometer on Mars because we knew it was going to be quiet on Mars. We know there's not plate tectonics like we have on Earth, where you get all of these earthquakes like the San Andreas Fault in California or many other plate boundaries you can see around the world. We know we don't have that sort of production of quakes on Mars, so we knew it was going to be quiet, and so we wanted to make the most sensitive seismometer we could. And so, in scientific notation, we were looking for things that were nanometers per second squared sensitivity. If you're thinking if you convert that's acceleration terms. If you think about that in terms of what the actual motions are at the frequencies we're looking at motions that are approximately the scale of a hydrogen atom. So this is an extremely sensitive instrument. So this kind of black bar right here, it was our target sensitivity. In reality, we actually our sensitivity is more like this little black dot here. We've actually done better than we expected. We put in a lot of uncertainties on how well things were going to behave by the time we actually deployed it on Mars, and we've actually gotten better performance than we wanted. So this is a tribute to the instrument designers and the engineers that made this happen. But when you're doing something this sensitive, you have to really understand all the other things that are causing signals in the instrument. So we need to understand the intrinsic noise of the instrument, but the instrument is also a really good thermometer. It's also a good wind sensor. It's also a good pressure sensor. It's also a good magnetometer. So we need to correct for all of those things, which is why we have our weather sensors, et cetera. And the other thing we do is try to minimize exposure to all of those things. So this, these kind of floating metallic looking things here, this is actually the actual sensors themselves for the very broadband sensor. These are tilted pendulums, so they're all measuring motions at an angle of 30 something degrees. And we have 3 of those, and from that we can reassemble the whole 3D motion field. But those are, in order to keep those as isolated as we can, we surround them with a lot of stuff. So first we surround them by a vacuum sphere. For those who follow closely Mars missions, you might know that we were initially going to launch in 2016, but this sphere here was continually developing leaks. It got fixed pretty rapidly, but not to the point that we were confident to launch in 2016. So we had to wait the 26 months for the next transfer orbit. And so it ended up launching in 2018. Around that, we have another thermal enclosure that actually contains atmospheric CO2 to give another layer of protection from thermal changes. And then on top of that, we have the wind and thermal shield, which gives another range, another layer of thermal protection, and has this actually a skirt that drops down the bottom, which is actually chainmail. We had somebody make us high quality chainmail to get as good a seal around the bottom as we could. And that shields us against the wind and it gives us an extra shield against thermal variations through the day. So that was all done. It turns out installing a seismometer on Mars is really challenging robotically. This goes back to some of the things that were talked about early in the meeting. A person can install a high quality sensor like this in a day. It took us quite a bit longer to do it, with sending commands and then waiting to see what the results of the commands were, et cetera. So off here on the side, there's a video. This is showing the instrument context camera through time. We had to put we had to look at the ground, figure out where we could put the instrument, then we place the instrument in our best desired location. And then we release the tether so that that's not waggling in the wind. And then we open this thing called the load shunt assembly, which is trying to separate the seismometer from motions and the tether. And then it took us quite a bit of time to try to open up that load shunt assembly. That took multiple tries. Finally, we got that well open. And then once we were happy with that, then we bring in the wind and thermal shield and place that on top and adjust that and make sure we're happy. And on Sol 70, we released that and we had a fully functional seismometer doing exactly what we wanted it to do. So 2.5 months to do something which a human being could do probably in a day on Earth, and maybe in a spacesuit might take a little bit longer, but certainly could be done more efficiently with a person, but not necessarily more cheaply. So over here on the left, there's some images of that load shunt assembly that we had to open. It took us a little bit of time to pull that open. This is what it ended up looking like once we got it open. And this is also a picture of once we had the wind and thermal shield on top. One of the questions people often ask if they know anything about seismology is, what can you do with a single station? On Earth, we always use networks. It turns out when you have a Mars
5 minutes.
Okay, I'm talking too long. Okay, so we managed to locate some events by looking at PNS waves. We have lots of events recorded to the mission, mostly in this quiet evening period. These days, it's actually very noisy in the evening, and so we've only seen a handful of events since July. Here's one of the events. They're messy compared to Earth events. This is our largest event. You can see here where the PNS waves come in, and also one of our banes of existence, these things called glitches. Once we locate the events, we have these. We have two of them located right in a place called Cerberus Fossae, which is very exciting. It's a place that was that's got the youngest, some of the youngest volcanism on Mars, and so this was really exciting. I want to just real quickly point out that we had a lot of problems with the heat flow probe. It first backed out, and the engineers have done wonderful things. We pushed it down with the scoop. So here's some videos showing that. As of right now, we've got it successfully buried, but the next steps are still up in the air. We're going to scrape some more material on top of it, but we don't know exactly whether it's going to make it down or not. And I'm sorry I did not budget my time well. There's lots more to talk about here, but this is some of the fun engineering challenges we deal with. So just to summarize, it's hard to do this by robots, but we have seen Mars quakes and we've learned more about the interior, and we've learned more with our secondary instruments, and I'll stop there.
Okay, great. Just a reminder for everybody that we do have a Slack set up, so if you want to ask some more questions, I know you kind of rushed through some of those instruments there at the end, so I'll try and get to a couple questions here while we have some time. The first one was, I know there's only one seismometer, but how does that compare to terrestrial seismometers?
Yeah, so the quality of the seismometer, our best seismometer, is fairly equivalent to the best seismometers on Earth. So these are the kind of instruments that you install, and high quality observatories often like dug deep down into the ground to make them as quiet as possible. So it is a very high quality instrument, comparable with the highest quality we can get on Earth.
And you mentioned how sensitive the instrument was. Are you going to be able to detect landing of future rovers?
That's a good question. So we have people actively looking into that. It's what it looks like right now is so when Perseverance lands, we probably won't see anything directly related to the landing. It's possible we may see the shock wave from the entry, descent, and landing. Jezero Crater is a long way away from us, so we're not going to see anything directly from the landing. We had hoped that maybe we'd see the ballast mass, but that's likely below our noise floor.
Gotcha. And do you have any work that you've done on maybe improving the deployment of robotic sensors? Maybe using AI for the future? You mentioned how difficult it was to get that first seismometer replaced.
Yeah, I mean, I don't know if there's much to be done for AI. I mean, this has to be an interactive process. I mean, that's really why it took so long, is because you do one thing, you plan the command, you send the command, it takes a day before you can see the results of it, and then you have to digest that information and think about what to do. I think I'm sure you can come up with ways to use AI to speed that up, but AI is, and any of these things are trying to replicate a lot of the things that people can often do quite easily. And so it's still probably the most efficient way to make sure that we're doing things correctly is to just do lots of these ground in the loop decisions, which is why it took that long. I can't imagine that AI would be hugely changing in that. There are things to think about in the future for other places to think about ways of using smart processing of the data before we send it back, because we're often limited by how much data we can send back, which will become a bigger problem if we think about doing seismology out in the outer solar system.
Thank you for your time.
Yeah, sorry for not leaving enough time for questions. I apologize for that.